Hello, welcome to our AP Physics 1 pre-flight on relativity and black holes. This is an extension of the universal gravitation unit, meaning that you as the listener should have everything figured out up until this point. I'm Leonard Krueger.
I'm Hasan.
And I'm Minarro.
In this we'll be focusing on Einstein's relativity theory, as well as properties and mathematics about black holes. So this first slide will focus on Albert Einstein's relativity theory. In 1905, Einstein determined that the laws of physics are the same for all non-accelerating observers, and that the speed of light in a vacuum is independent of the motion of all observers. This means that when an object is traveling at light speed, it is moving only through space and not time. To put this into perspective, if humans were ever to achieve interstellar travel at light speed, this would mean that they are traveling through time. For example, the star closest to our solar system is Proxima Centauri. Let's say that we send a team of astronauts there in a spaceship capable of travel at light speed. For this scenario, let's say it takes 8 months to accelerate and 8 months to decelerate. For the astronauts, the journey would take 16 months, while it would seem as if they were gone for roughly 5.5 years from the perspective of someone on Earth. This is due to the fact that while they are traveling at the speed of light, the astronauts will only experience space, not time, while the people on Earth will still experience both dimensions.
Now we will make the transition to black holes. A black hole is defined as a region of space-time from which an extremely strong gravity prevents anything, including light, from escaping. Black holes are created when a large star undergoes an explosion, also known as a supernova. If the star has a mass that is 3 times of our sun, it has a chance to implode and create a black hole. When this happens, all the matter from the star is condensed into an extremely small area, causing the black hole to have an extremely large gravitational pull.
On this last slide, we will focus on some key calculations that can be made with black holes, using your knowledge from the gravitational unit. The first concept is the Schwarzschild radius, which is the radius of the event horizon to the center of a non-rotating black hole. The event horizon is the closest any form of matter can be to a black hole without being consumed by its gravity. The Schwarzschild radius is equal to 2 times the gravitational constant times the mass of that black hole over the speed of light squared. The second concept is that escape velocity, which is the minimum required velocity to leave an object with mass. When talking about black holes, the escape velocity is extremely high. This is because we must set the kinetic equation equal to the force of gravity equation, and then after being reduced, you will get velocity, the escape velocity, equal to the square root of 2 times the gravitational constant times the mass of the black hole over the radius of the black hole. And since a black hole has an extremely large mass and an extremely small radius, the velocity will be extremely high. These are the sources we use, and thank you for watching.